Okay, so welcome to the second afternoon session. I hope you all had your coffee and are still fit and awake. The session is about software, and I would say that this topic is quite general, so you might have seen more specific topics at some of the sessions. But the reason might be that you're really touching into, well, three different topics of software security with three different talks. It's about high assurance software, it's about obfuscation of software, and it's about masking in software. So I think that might really cover the most important topics in software for CHES. So let's get into it. The first talk is about high assurance serialization, and the speaker is Santiago.
Thank you very much. So this talk is about securely erasing leftover secrets on the stack and in registers after a cryptographic routine is done executing. This is a collaboration between these 8 people. My name is Santiago Ransolmos. We implemented this feature in the Jasmine compiler. And Jasmine is a programming language to write high-speed, high-assurance cryptography. This talk has 3 main takeaways. The first is that Jasmine makes erasing your secrets after you're using them easy, that is automatic, secure, that is formally verified, and efficient. The second takeaway is that erasing your secrets after you're done using them in mainstream languages is harder than it should. The main reason is the way that these languages are defined. Local variables, for instance, do not exist after a function returns. And the third takeaway, and last, is that serialization, such as many security mitigations, require cooperation between the language and the compiler. The problem we tackle in this work is easy to state. Once a cryptographic library is done doing its thing, it needs to clean up and remove all secrets, traces from memory and registers before going back to user code. This is important because from application code, we can recover the secrets otherwise, either directly or through side channels. And we cannot trust this data to be overwritten by the operating system after the allocation. Indeed, in previous work, Cho, Pfaff, Grafik, and Rosenblum studied the lifetime of 20-byte stamps placed in memory in several laptops and led to use daily. And they show that this data, they can recover this data days or even weeks after daily use. Nevertheless, cryptographic libraries usually ignore or fail to address this problem. In our work, we study 10 cryptographic libraries and conclude that none of them achieve serialization fully. We classify them in 4 failure modes. So first are libraries that make no attempt at serialization. There are libraries that attempt to serialize their data, but fail because the compiler optimizes that code away. There are libraries that only serialize inputs to their API. And there are also libraries that serialize only secret data visible from the source code. So libraries such as BeresSL and Ring make no attempt at serialization, and they recommend that users overwrite the stack with garbage data after the library is done. But this is really tricky because then users need to estimate how much stack each call site needs. Then there are libraries such as TinyDTLS and NSS that attempt some serialization of their secrets, but for instance, using memset or direct writes to memory, compilers usually see through this, see that this is not part of the functionality and optimize it away. There is a paper from 2017 that called Dead Store Elimination Still Considered Harmful, where they show an attack on NSS that leaves secret key material after it's done executing. Most libraries today, such as NewTLS, libsodium, EmbedTLS, WolfSSL, and OpenSSL, manage to achieve serialization through several tricks to hide this from the compiler and to avoid optimizations. But they only apply it on their API inputs, that is the message and the key, for instance, but they do not do so with local variables, with arguments to local functions, which are also secret and left on the stack. In our work, we present a small proof of concept client of the library with a memory corruption bug, and we're able to recover the secret key from a call to libsodium. Lastly, there is a library which is written in Rust called Dalek, and that it achieves serialization of all secrets in the source program. This is possible in Rust because you can inject some code that gets run after each object goes out of scope. But this is still not enough because the compiler again gets in the way and it introduces spills. It abides by a calling convention, so there are callee save registers that need to be saved. It caches common sub-expressions of different parts of the program and introduces copies for alignment and so on. The pattern here is clear. Reliably implementing a security mitigation in software is not possible if the language is not expressive enough to capture the problem, or if the compiler cannot distinguish between functionality and mitigation. In fact, for C compilers such as GCC and CLang, there are plenty of features requesting things like serialization and plenty of proposed patches. Here, there are a few examples also from Rust and OCaml, but the vast majority of these proposed patches get rejected immediately because it is not possible to state the problem of serialization in terms of the C abstract machine, because once a function is done executing, this data no longer exists. And this means that reviewing the code, writing generic tests for it, and integrating it in different contexts is really, really difficult. The most comprehensive work we could find about serialization is called What You Get is What You See, that proposes 3 strategies for serialization. And interestingly, a couple months ago only, GCC introduced a function attribute, strub, that performs per function serialization, which is similar to the simplest strategy that they present in this work. In this work, we implement serialization for Jasmine for whole programs. Jasmine is a low-level programming language. It is somewhere in between C and assembly. So here I have a snippet where f is a function that returns a 64-bit result in a register. It has a stack variable, which is 1 byte. There is also a main function that returns a 64-bit value on a register. It declares its own local variable s of 32 bits, calls f, and returns something. Serialization code for this kind of program needs to take into consideration not only the stack variables of main, this is the entry point, but also transitively all of its callees. The Jasmine compiler outputs code like this. It comes in 2 flavors, either a loop or straight line code, where you just override the secrets that the appropriate memory regions. In x86, we had the added flexibility of being able to write byte by byte, words, or even 256-bit chunks in AVX2. The advantage of doing this in Jasmine is that the Jasmine compiler is formally verified, and therefore, to integrate serialization, we had to provide a machine check proof that serialization does not introduce any bugs, and also that after a function executes, no traces of secrets exist either on the stack or in registers. This includes the key fact that other compiler passes do not interfere with serialization. In Jasmine, there is dead code elimination, the same way as in GCC, but this pass cannot remove serialization code because serialization code is a mitigation, it's not functionality. Another advantage of implementing this in the Jasmine compiler is that we can integrate the serialization threat model, which is that an adversary gets access to the stack and to registers after a function is done executing, with standard security models, for instance, cryptographic constant time. Cryptographic constant time is the baseline defense against time inside channels. It basically states that conditionals, like here, if secret equals 0, or memory accesses, like here, A of secret equals X, should not depend on secrets. And with this, we can combine these 2 threat models and show that compiled Jasmine programs resist attacks from adversaries that get to observe timing behavior during execution and get to examine the stack contents and register contents after execution. There is also extensive work in Jasmine on speculative side channels, that is Spectre. Here, the combination is not so easy because a speculative attacker can mistrain the branch predictor to early exit the serialization loop, therefore leaving some secrets in memory. However, the solution is straightforward, just standard memory synchronization fences solve the problem. We evaluate our solution in libjade, which is a crypto library written in Jasmine of standard cryptographic algorithms such as CHES, Poly, EX25519. And it also has some post-quantum crypto there. In this work, we focus only on Kyber, so the CAM that is now being standardized as MLCAM. libjade has side channel mitigations, timing side channel mitigations, and also Spectre V1 and V3 mitigations. Our benchmark show that the overhead of zeroization is less than 1.1% for standard crypto of reasonably large messages. And for Kyber, that is keygen, encapsulation, and decapsulation, is below 3.25%. So in summary, the immediate takeaways from this work are that Jasmine allows you to erase your secrets after you are done using them easily, securely, and efficiently. We have machine check proof that this is correct and that this is secure. Also, we can combine it with other standard threat models such as constant time and speculative constant time. And more generally, the higher level moral is that obtaining robust guarantees on security issues for software requires the language and the compiler to be security aware. And that formal methods, such as verifying the Jasmine compiler, make it feasible to obtain these guarantees. Thank you very much. Now I can take some questions.
Yeah, thank you for the talk. Other questions to be taken at the microphones in the middle aisle? So maybe one question, obviously the zeroization only works within the Jasmine scope. And as you said, there are libraries written in Jasmine. I presume that they get the secrets passed into them from the outside?
Yes, so these libraries are compiled, so you can compile the library with zeroization enabled, and then any secrets that they get will be erased. Or you can compile everything together as a whole program, the library as well, and then that also gets covered. If you want to link it, but you didn't compile the library with zeroization enabled, then there won't be zeroization there.
Are there I/O functions in Jasmine so that you can actually load data from file or something?
Yes. So there are two things. So first, automatic zeroization, you have it for your local variables. And then if you want to do it explicitly for arbitrary memory regions, you can also do it, and you declare it as a security mitigation, and the compiler will not touch it. Okay, so you can do it explicitly, but also automatically for your local stack and local variables.
All right. Any other questions? I don't see any. So I thank the speaker again. Thank you.
Thank you very much.
And then we get ready for the second talk. So as promised, this talk is about obfuscation of software. And the speaker is Alexei. Please take it away.
Thank you for the introduction. So this is joint work with Darius, Vietsang, and Mathieu. Let's start with a quick introduction to the topic. So as you might know, cryptographic code obfuscation is a very useful primitive that could potentially help to do things like mobile payments or digital right management. It has many other applications. And one of the prominent examples is white box cryptography, where we try to obfuscate a symmetric encryption, for example, to make a public encryption out of it. And the main idea here is that we want to obtain some program that has the same functionality so that we can run it and encrypt things, but we cannot extract any key from this program. So this program looks unintelligible to us. More generally, we want to obfuscate not just ciphers, but any program, any business logic with any potentially secret values in a way that is still being possible to run and still not possible to extract any information from it, neither about the values nor structure. And of course, we don't want just to have some ad hoc solution. We want a cryptographic strength from such primitive. And the state of the art is that there are two directions for white box cryptography from initial designs from 2002, which are practical and fast to execute in practice. And there is a theoretical obfuscation, the notion called indistinguishability obfuscation, or IO in short, which recently had a breakthrough where they showed that it is possible to obtain obfuscation based on reasonable assumptions. Unfortunately, white box cryptography is practical but totally insecure. So here I list one attack on the initial construction, but for more attacks, you can attend the sessions tomorrow. And the theoretical obfuscation is secure but not practical because of the large amount of abstractions needed to prove things. This is not feasible to run in practice. So I want to focus on this problem that we want to have something that we can run, but we cannot look inside. And in practice, for applications, we don't really need it to be software, although this is a software session. In real life, we have, so for CHES participants especially, it should be more familiar that we have such topic as hardware security. There is whole industry. There are various digital circuits, smart cards, secure tokens, or even secure coprocessors where we can even run some sort of operating systems inside them. And this is presumed to be secure in a way. Maybe it's not totally impossible to break, but it's at least expected to have high cost of breaking these things. And here we have the whole range of functionality and complexity of these things. And of course, with larger functionality, there is larger attack surface. And it means that it's essentially becomes less secure because there is higher chance of it to be broken. And how the two things are connected. So there is work from TCC 2010, which shows how to achieve program obfuscation. So this primitive that we can run programs without knowing what's happening inside, using a stateless, simple hardware token, which should be tamper-proof from physical perspective. And just to give you a rough idea of how it works, is that we have a developer who wants to obfuscate, let's say, a program, and it performs some manipulations and sends to the user, who also has some hardware, which allows to interact with hardware with this manipulated program and to compute inputs and outputs. And this work was from theoretical perspective and not really useful in practice. So in this work that I present, we explore the design space and try to generalize it and focus on performance so that it's really feasible to run in real life. It's more user-friendly, it doesn't require any specific knowledge from the developer or from the user, but also focus on the security, potential security when this should be implemented in hardware. So I present in the obscure, the versatile framework for obfuscation with a secure element, where our contributions include a compiler from a subset of C code to an obfuscated or sort of encrypted bytecode. We generalized instruction set, while the initial work considered only Boolean circuits. In practice, this would be too slow to use, so we use 32-bit instructions. And we also group instructions together to amortize communication with a secure element, with the hardware device. And this in turn requires development of specific algorithms to group these instructions automatically without involving interaction with the user. Furthermore, we propose a new universalization technique, which allows to hide the whole structure of the program. Because originally, only the instructions themselves or the values are protected. But if you want to protect the structure of the program, any kind of logic, then you need to apply universalization, which I'll talk about later. And finally, I will describe some applications of our framework. This is not work of this kind. Before, there were, for example, Opuscuro and Iron, who the schemes required to be running inside SGX, so which, as you might know, had numerous security problems, and for example, was recently deprecated from consumer devices. So now you can only run it in a server. There were also another schemes such as Phantom, Ghost Rider, and Hop, which did something similar, but they required a fully fledged CPU, secure CPU, physically secure CPU, and they used also Oblivious RAM, which is a quite a heavy primitive and also involves more complexity. So with our scheme, we try to stay on the left side of this range, maybe to have restricted functionality or performance, but having bigger potential for secure hardware design. So I will now recall the scheme from TCC 2010. In this scheme, the developer has a code that wants to be sent to the user who has a specific secure element. And one way to achieve this is to have public encryption so that the device has a private key and the public key is available to everyone. And the developer simply encrypts the program with the public key, sends to the user who can communicate with the device this program and lets the device decrypt the program internally and then evaluate any queries from the user by evaluating this program. So as you might see, we are not really doing any obfuscation. We're not like renaming variables or changing the control flow. This is more like encryption or delegation of computations. We are saying obfuscation because this is term for the goal of what we want to achieve, but not how we achieve this. The problem with this simple scheme is that we cannot, because the device has to be fixed size, we cannot evaluate arbitrary large programs on it. So we want to somehow split programs into smaller pieces and reduce the functionality of the device. And the scheme from TCC 2010, first of all, it focuses on Boolean circuits. And the idea is to perform computation of each gate separately using the secure element. So another way to view this is that we split the encrypted program into pieces and put pieces to the device in some order. And then the device has some communication loop where the benefit is that this communication does not have to be secured. The way it looks internally is that besides this blue key, which is needed to decrypt the program or the gates in this setting, there is also internal symmetric key, which is pink in this figure, which is used to encrypt all intermediate values. So we have in the device, we need to have functionality where in the input, we have two encrypted values and also an encrypted gate. And the device has to decrypt all these things in a secure way, compute the result, and encrypt the result and give it out. If you just give this functionality to the user, it won't be secure because the user can apply arbitrary instructions in different order, not in the way that the developer intended. So to prevent this sort of so-called mix and match attacks, we need to authenticate node labels. So for each input and output, we need to authenticate the gate from which they originate. And also the instruction should contain information from which gates it should take the inputs. And then the secure element has also to check that it has the right input corresponding to the instruction, and also encrypt information about the output. We also need to authenticate the full input so that the user cannot swap intermediate values from different inputs. And similarly, we want to authenticate the whole program so that the user cannot swap intermediate values from different programs. So these are just some technical details. And the scheme also suggests to use hybrid encryption, which means that we, instead of encrypting every gate with a public key encryption, we only encapsulate some symmetric key, and then use this symmetric key to encrypt all the gates. And there are more technical details omitted. So besides this evaluation query that is described here, that is the main thing, there are also 4 or 5 additional queries that are needed to make all this work, specifically to encode the input or to decode the output and so on. But I will not go into details now. So now we present our framework. On high level, it consists of a compiler, which takes a C program or subset of C and compiles it into obfuscated or encrypted bytecode, which is then sent to the user, who has an interpreter, which takes some input from the user, communicates with secure element, and produces some output. The interpreter doesn't have to be secure, it just coordinates communication with the hardware device. So, for example, to show you that we actually can obfuscate real C programs, this is one example of what we tried, is a function that computes sum of the input array. We only support subset of C, so the main constraint is that we don't allow data-dependent control flow, so we don't have variable length loops, for example. This means that the length of the loop should be computable beforehand. And we only support 32-bit integers. There is a whole compilation chain that implements all these transformations, but unfortunately, I don't have time to go into details now. On the high level, the obfuscation process looks as follows. We start with this program P that is, through compiler, is transformed into a sequence of multi-instructions, which are groups of instructions packed together, which are then encrypted using fresh symmetric key KS. And this is essentially the encrypted program that is sent to the user. In addition, this new symmetric key is encrypted using the public key of the device. And then this is given as a header to the program. So in one of the contributions, we group the instructions together. So if you have a program that consists of a sequence of instructions, instead of sending instructions one by one to the device, we group them together in an automatic way in order to reduce communications with the device. And here the idea is to have as much as possible shared inputs between the instructions so that they can fit together. There is also a concept of memory, but there is no memory inside the device. Memory is just the concept for the interpreter to arrange the communication with the device and to store the intermediate values. As an example of how this could work, first we query the device with the input, unencrypted input, and the device produces encrypted input, so encrypted with internal key. Then we pass this encrypted input to the next instructions together with the encrypted multi-instruction and the re-encrypted symmetric key, which allows to produce the encrypted output of this sequence of instructions. And after doing this a few times, in the end, the final multi-instructions, they contain a flag that says that the output should not be encrypted, and evaluating the final instructions gives output in the unencrypted form, and the user can obtain the output. And this shows how the evaluation query works inside, and this is very similar to the figure showed before. Here I noticed that we use authenticated encryption because we need to also prevent manipulation of the ciphertext. Finally, I mentioned that we described new way to universalize circuits. And the idea is to embed any initial circuit of multi-instructions into this rectangular shaped structure, where there are rows of parallel applications of multi-instructions intertwined with permutation networks. And because all the internal flags are encrypted, for the end user, there is no way to distinguish one such network from the other. Finally, I'll describe some applications and benchmarks that we performed. For the sake of benchmarks, we defined four sizes of secure element that we need, from small to extra large, and they range by the number of inputs and outputs in one multi-instruction, and the number of instructions, so small instructions inside the multi-instruction that is performed. And we estimated performance on this small microprocessor, Cortex M3, which has 120 megahertz. But this is only for benchmarks. In practice, with hardware, the performance should be much better. First, we rated the design in the white box mode, which means we encrypt the instructions, but we don't apply the universalization. So for obfuscating the IS cipher, we see that we go from 5,000 original instructions in the bit sliced implementation into 30 to 300 multi-instructions. And the final evaluation should take around half a second on all sizes. Traceable IS has a sort of watermark built inside and essentially requires two calls to the IS. So it's just twice as larger, so it requires around 1 second to execute. And to show that we can obfuscate or protect arbitrarily sized programs, we also apply this to neural network for recognizing handwritten digits. So the standard one from MNIST database, which has originally 200,000 instructions, which are then transformed into a few thousand of multi-instructions in our framework. And this still is feasible to execute within half a minute on these devices. We also tested full obfuscation mode, where we hide the whole structure of the program. So we embed it inside this rectangular shape, which adds a whole magnitude of slowdown. So for IS, we get an order of seconds needed to execute such a program. For example, for computing sum of 1,000 elements, we need from 10 to 40 seconds, and similar values from finding maximum value in the size of array of elements of 1,000 elements. And I recall that all these programs, if the user gets them, the user only sees the rectangular shape and have no idea what these programs do. To conclude, we proposed an obfuscation framework with provable reduction. So we provide security proofs that if the secure element is not temperable, then we get provable security, black box security of the obfuscation. We provide compilation from C programs, which makes it more user-friendly. We provide new technique for universalization. And we also provide an interpreter and runtime simulator to show how this thing should work. So we only require stateless and light with hardware elements, so it should lead to very small attack surface, but it is still an open question how to actually perform the hardware design and how to protect it from physical attacks. I invite you to look at the code or read the paper in details, and thank you for your attention.
Yeah, thank you for the talk. Other questions? Maybe, oh yeah, there's somebody walking up. Nice.
So it may be that I'm just misunderstanding here, but from my naive perspective, it looks to me like what you've done is designed a VLIW processor with encrypted instructions and encrypted memory. Am I understanding this right?
I'm not sure what you mean by encrypted memory.
Well, I mean, it encrypts the data on the way in and the way out, right?
Yeah,
Yeah.
it can be just a circuit that doesn't have to store any memory.
Okay, sure. But it still looks to me like it's essentially a VLIW processor, but with everything in the processor except, you know, the ALU and decoding removed from it. Is that right?
Yeah, sorry, I don't know about the VLA.
Like very long instruction word? It's the packing method, so your mult instructions look like VLIW packets?
Yeah, I suppose, yes. Yeah.
Okay.
But we don't work with it. We don't, as you can see, we don't design actually the processor. We design just it's more about the protocol or the compilation from the C code toward this packets, as you say.
Okay, thank you.
Hi, thank you for the presentation. So if I understand, the secure element is required at each execution of the obfuscated code by obscure, is it?
Yeah, it's queried for each multi instruction essentially.
So which kind of product maybe embed obscure for which kind of applications product? Because it's a constraint to have a secure element with the CPU at each execution.
Sorry, you mean CPU?
Yeah.
Yeah. No, our goal is that in principle this doesn't have to have CPU inside it. It's secure and that we run it. It could be just some hardware circuit that in one cycle just computes all the encryptions, decryptions, and the computations inside.
Okay, and you guess it's for like IoT or big server, which kind of product may embed obscure?
So I mean, we didn't think about concrete products.
Okay.
We want to just have a general purpose obfuscation from C programs.
Thank you.
Hello, so it was very interesting. If I correctly understood your talk, you said that in your subset of C, you support only control flow instructions that are not data dependent.
Yes.
So with regards to your introduction, where you said that you want to support to be able to obfuscate any program, it looks like a strong limitation. And how do you have plans to support more generic data flow, control flow? Is it a limitation?
Yeah, it is a limitation given by that we want to stay really on the left side of this hardware range, that we don't want to have a CPU, for example, inside like the other schemes like HOPE and that I mentioned, which also involve additional techniques for protecting such schemes. For example, if you have some jump instruction or you have instructions that take different time to execute, you need to have a different range of countermeasures, which would also have own set of problems and attacks. So we wanted to really reduce the surface, so we don't do this. In principle, what we could do, so we support ternary operation. So we have sort of data-dependent ternary operation, but in the end, we compute both cases and then choose which of the case to take as an output.
Okay, thank you.
Any more questions? Or are we all satisfied? Okay, then thank the speaker again. Then we're getting to the last talk, which is a pre-recorded online talk. Is the technical setting fine with starting the video? So this one is about masking and
Hello.
software.
Everyone. Today I'm here to talk about our paper titled Efficient Table-Based Masking with Pre-Processing. First, I will introduce the background of our research. Next, I will present our new TBM scheme. Then I will demonstrate its application. Finally, I will conclude with a summary of our findings and discuss future directions for this work. First, I will cover the background. One of the most common forms of side channel leakage exploits the correlation between sensitive data and power consumption. Such side channel attacks have been effectively used to recover sensitive information, like secret keys, by analyzing this correlation. Masking is a promising approach to protecting against this type of side channel attack. A TBM scheme starts with splitting a secret X into D+1 shares using random variables, such that the sum of all these shares recovers the original secret X. The scheme then recomputes all lookup tables successively. Each of the mask table maps m bit to m bit. Finally, the output shares are produced, which are functionally equivalent to the original S-box. Here is an example of TBM with m equals 2. It takes the original S-box some variables and D+1 input shares as inputs and outputs D+1 masked lookup tables, which can securely execute the original S-box. Masking techniques such as TBM and other schemes often introduce large overhead and typically require a large number of random bits. However, several works have proposed a paradigm in which computation is divided into two distinct phases, pre-processing and the online phase. The pre-processing is independent of the input variables and produces some pre-computed variables to be temporarily stored, for example, in the RAM. It can be performed in the device idle time, such as when the IoT device is waiting for the data of authentication or response. The subsequent online phase combines all the input and the pre-computed variables to calculate the output more efficiently. This pre-processing paradigm can lead to significant performance improvements, making TBM a powerful tool for enhancing security against the side channel attacks. As shown in this figure, the blue section represents the pre-processing phase, while the green section represents the online phase. In the pre-processing phase, it mainly recomputes D+1 masked lookup tables T0 to TD using secret shares head X of 0 and head X of D-1. And only the last masked lookup table and some pre-computed variables need to be used in the online phase. It simply acts like the original S-box to get the head Y of D. Typically, head Y of D explores these pre-computed variables to recover the final correct output. Before introducing our TBM scheme, I will provide an overview of Sharam and Paris scheme and Cora scheme. Let's briefly revisit the Sharam and Paris scheme with m equals 2 and d equals 2. Their scheme first generates two random values, s of 0 and s of 1. The scheme then constructs a new lookup table simply by exploring s of 0 and s of 1 with the original S-box S. Following this, the elements in this lookup table are shifted for 2 rounds using head x over 0 and head x over 1. Finally, the last lookup table with s of 0 and s of 1 are used during the online phase. In the online phase, it takes head of 2 and the mask table T2 with the random values s of 0 and s of 1 as input to recover the original s of secret X. However, this scheme has vulnerabilities. As we can see, the random values are shared among all the mask tables. For example, consider the scenario illustrated in this figure. Assume that head x of 2 not equals 0. Let's say it equals 1. In this case, the joint leakage of head y of 0, head y of 2 and T0 of 0 depends on all input shares, which are head x of 0, head x of 1, and head x of 2. Since head y of 2 XOR T0 of 0 XOR the original S box S of 0 equals to S of all sum up of head x. Note that the original S box S can be considered as a public variable. Coron addressed the above security flaws by replacing each element in the lookup table T with D+1 shares and refreshing the shares after each shifting operation. As depicted in this figure, Coron's approach replaces the lookup table with a matrix of sets 2 to the power of m times D+1, which is 4 times 3. During the refreshing process, it first generates D+1 random variables and element-wisely adds them to the input vector. In this way, the refreshing process enhances security as the same masks are no longer shared among different rows of the matrix. And the online phase is pretty much like a Shriram and Parrot scheme, which just takes head x of 2 and a mask table T2 as inputs to recover the original S of secret X. However, in the case of AES 128, Coron's scheme requires approximately 40 times D+1 kbytes of memory to store all the pre-computed tables. This is impractical in many real-world applications. Our scheme offers two key features. First, a small number of pre-computed variables. This allows for wider deployment of the scheme on devices with limited RAM capacity. Second, linear capacity of the online phase pertaining to the security order D. This results in a highly efficient scheme in terms of speed. We also significantly reduce the overhead of random bits generation, where the main timing costs lie in storing and loading operations to a buffer. Next, I will introduce our new TBM scheme. I will formally introduce our new TBM scheme. In a nutshell, our scheme involves encoding all entries over the unmasked lookup table and D random variables by a maximum distance separable encoder, or MDS encoder for short. And the code word completes the masked table, which is smaller than that in Coron's work. Thanks to the MDS encoder's property, the probing security is guaranteed, ensuring that any D elements in the code word are distributed independently over the unmasked entries. As in the definition, a matrix A is called an MDS matrix if and only if all the subdeterminants of A are non-zero. An MDS matrix can be constructed using a Vandermonde matrix built from A0 to AN-1. Then the n-d times D matrix A equals A prime bracket D to n-1, comma star bracket, dots A prime bracket 0 to D-1, comma star bracket inverse is an MDS matrix. This is the complete algorithm of our scheme called a masked table. Our scheme takes D+1 shares of head X and return D+1 shares of head Y. It considers a lookup table as mapping each element in the field of 2 to the power of m to an element in the same field. The MDS matrix is over the field of 2 to the power of 2m, meant that 2 to the power of 2m should be greater than or equal to the power of m plus d. In the pre-processing phase, a lookup table T0 is constructed first. The original S box S is actually equal to T0, with S0 simply being a vector of all zeros. Then it recomputes all lookup tables successively using head X of K, which is the shift operation. In the meantime, every round it will do a refresh operation. Eventually, this phase generates some pre-computed variables that are ready to be used in the online phase by 2 CHES part 1. And in the online phase, it simply uses the pre-computed variables and the head XD to generate the final output by 2 CHES part 2. Now, I will present a simple example to demonstrate our scheme. Same as before, consider a scheme with m equals 2 and d equals 2. An MDS matrix is constructed first. It has D rows and 2 to the power of m columns inverse, which is 2 times 4 inverse. The MDS matrix must, of course, satisfy 2 to the power of tilde m greater than or equal to D plus 2 to the power of m, which in this case tilde m equals 3. To map between the two different fields, we implement a function called field map that performs the mapping while keeping the homomorphism over addition. It simply removes the highest significant bit. In the pre-processing phase, masked table first constructs a table of vectors S0 of 0 and S0 of 1. Then the first lookup table is computed using the MDS matrix and the S box S. After that, the masked table refreshes and shifts the rest of the lookup tables by elements hat X using the packed shift refresh function. According to the MDS matrix property, it will keep the random values remaining fresh. And the masked table also makes sure each lookup table is constructed correctly. After decourse of packed shift refresh, the outputs from the pre-processing phase are transformed into the output shares using 2 shares. This constitutes the online phase. Here are the details of the packed shift refresh function. During the pre-processing, it first generates a random matrix R, resulting directly in a table of vectors S prime of 0 and S prime of 1. Next, it computes a temporary variable W, which is the result of the MDS matrix A dot R. The function then uses the MDS matrix A input vector S and W to refresh and outputs a matrix V, whose size equals to the MDS matrix A. However, after that, V is over the field of 2 to the power of tilde m. So the field maps between the different fields. Finally, it uses hat X of K to recompute the lookup tables through the shift operation. After decourse of packed shift refresh in the pre-processing phase, 2 shares first generates a random matrix R, resulting directly in a table of vectors, hat Y of 0 and hat Y of 1. And it is actually S2. Then it computes the temporary variable W. In the online phase, it uses these temporary variables W with S2, T2, and hat X of 2 to recompute the final output shares. Of course, the field map function is employed on V to ensure the correct computation of hat Y of 2. Since the masked table consists of decourse of packed shift refresh plus 1 call of 2 shares, its complexities for pre-processing and online phases are big O tilde m squared times 2 to the power of m times d cubed, and big O tilde m squared times 2 to the power of m times d, respectively. We compared our scheme with current scheme and a recent TBM scheme denoted as VV21 from the paper by its authors and year. Compared to the current scheme, our improves on both random bits and pre-computed bits. Compared to VV21, our scheme offers better performance in both pre-processing and online phases. As most masking schemes, including ours, require true random bits, the deployment should naturally target the microprocessors that contain a true random number generator, or TRNG. Basically, the TRNG can generate the required random bits and operate in parallel. In our scheme, as in this figure, the TRNG independently generates a batch of random bits and then requests an interrupt to the process, indicating that the random bits are ready. Subsequently, an interrupt handler stores the random bits in the RAM buffer. The program directly accesses the buffer when it requires random bits. Therefore, the storing and loading of random bits to the buffer dominates the overhead running time of the random number generation. As long as the buffer always provides sufficient random bits, that is, the program does not need to wait for the TRNG. Now I will present its application. First, I present a comparison table for TBM scheme of AES 128 with VV21 marked by the number 4 and AVV23 marked by the number 5. Compared to VV21, our scheme has a better performance of cycles for the pre-processing and analysis. Random bits are less efficient than VV21, and their RAM usage is slightly better than ours. Compared to AVV23, our scheme exhibits better performance of cycles for the online phase and random bits. Our RAM capacity is half that of AVV23. However, the performance in terms of cycles for pre-processing is lower than that of AVV23. I also present our t-test results from left to right. It shows in first order when TRNG is on, our scheme is secure, and it turns out to be insecure when TRNG is off. The last one is the result in second order when TRNG is on. As the security order D equals 1, so it is not secure. In the end, I conclude our new TBM scheme and talk about some future works. In this paper, we introduce a new TBM scheme that is more compatible with the pre-processing paradigm. Our scheme is designed to address the challenges of available RAM size for pre-computed variables and the speed of the online phase. Both the theoretical asymptotic analysis and the applications to AES in practice show that the scheme is specifically tailored to optimize the utilization of RAM resources for pre-computed variables, while maintaining efficient execution during the online phase. The security of our scheme is proved rigorously and validated by performing t-test evaluation in practice. We conclude our proof by analyzing AES 128. All TBM schemes remain vulnerable to some dedicated side-channel attacks exploiting the repeated use of shares. A notable instance of such attacks is the horizontal attack. The random probing model can effectively capture repeated leakage of shares, so we believe proposing security TBM schemes under the random probing model in the future is of great importance. We also believe a promising future work is to investigate the masking scheme in the pre-computation-based paradigm for the protection of other crypto systems, such as post-quantum cryptography. This concludes my presentation. Thank you all for your attention and for your listening.
Yeah, thank you for your presentation. So the authors are available in the Zoom room, and we might have audio even. So if there are questions, we could have some kind of remote interaction. Are there any questions? Okay, then maybe just a small question from my side. What hardware do you use to do the evaluation? Can we get the Zoom audio? Usually not. One second. All right, so there's no audio, of course. Okay, then I guess I'm sorry for the authors that I guess answering questions is slightly inhibited. If you have any questions, please write emails to the authors, and I'm sure that they will respond in good time. And otherwise, well, there's just another break coming up, and there's a poster session outside, so please enjoy the posters. And one more thank you to the authors, please.